So this video is going to be about anti-aliasing, which actually is a pretty big deal in computer graphics, right? You want to get something to look very polished, looks very accurate, very professional. Anti-aliasing is a must for your renders. So what is it, right? The word is anti-aliasing, and obviously it's kind of it's some technique that try to eliminate aliasing. What is aliasing though? Like, what does that mean? So why don't I show you by trying to make this thing less crazy, right? This is just a code that I copied from last video. Let me just only have one P light, which is right here, and let's make it stop moving. So vec 3 0 0 1 0. So there we go, and make it monocolor, so probably white like this. I want to make it 100. Okay, it's pretty bright, which is good. Might be a little too bright. So, anti-aliasing. Let's just tune the scene to optimize for what we're actually looking at. God damn it, what's going on with the editors? Okay, wait, do you see that? Okay. I think it's because I pressed delete and, well, that's weird. So, this is our scene, and it's a lot of cubes floating around. Why don't I just change that? Get rid of the extra geometries just to demonstrate to you what's going on here. Now, what's actually going on. All right, that actually looks pretty cool, right? Make something great out of it. So let me raise the light up a little bit. 2, 3, 5. It's still a bit. And let the camera stop spinning, or just fix it at a certain time. What if it's 9? Okay, I think that's good enough. So aliasing, what is it? You know, aliasing tend to happen in the edges or the highlights. So here, what the term means is basically, let me just illustrate a little bit. So aliasing, it's a term that originated from the signals theory, which we're not going to. That's too big of a preface to what we're talking about here. So aliasing, what is it? Now remember, in the very first video, I think it's intro to shader toy or something. So remember that your monitor is represented by a 2D array of pixels, right? And remember what we did with the rendering system. Say the projected image of a circle, I mean a sphere, onto the screen, something like this. Okay. All right. What we did, remember, was to shoot a ray through the center of each pixel, then use the color that the ray returns to light the pixel itself. Right? So let's just do this. All right, these returns the right colors. Obviously see. I'll just try to be a manual rasterizer. And this ray is outside of the thing. Okay, you can start to see why there's jagged edges. Right, this is outside. It's also outside really close though. You know, but with the method that we're using right now, we don't care. So you basically get something like this, right? Okay, so it's like here. Basically get two grids on top. This is kind of the circle that you get, even though it's not exactly what you wanted. Not exactly a circle, right? Not exactly a circle. So this is kind of the shape that you get if your pixels are big enough. So what's the problem? What is the problem here? The problem is that we're assigning color to the entire pixel. So in each pixel, the color if all of its area must be uniform, which is not true um, if you want to project a picture perfectly onto the camera, right? So what people tend to do is to make the resolution of the frame buffer or the monitor really big, so that these pixels are really small that the human eyes can't notice them, right? At the point that we are right now, obviously we still have some issues with the resolution, right? So you can see there's some jagged edges here. If I take a snippet really quickly, just to use it as some kind of magnifying glass. All right. So here we go. For some reason, Windows likes to take a long time on these simple operations. So you can see that even though it's supposed to be a straight line, there's jagged edges here and there, right? So clearly, there's some aliasing going on, and this corresponds to what I'm telling you right here. Because rendering process is fundamentally discretized due to that the screen is divided into small pixels and each pixel is a square. What you should be doing in order to anti-alias it correctly is, instead of just shooting a ray through the pixel, right? So imagine this is the thing. You're only shooting a ray out of the pixel to get the color right. So the ray shoots where the fucking point of intersection is. You use the point of intersection to calculate the color. Well, what is a way better method, a superior method, to get anti-aliased images is to, instead of shooting a ray, you shoot out kind of a cone, right, with the cross area of the pixel's square that's projected out onto the scene, and compute the whatever intersection or missed portions of the cone. You essentially compute that down to an average color for this pixel. So you're kind of doing, say, half of the pixel is covered by the sphere, but half of it is not. And if it's not covered by a sphere, you return black, whatever. And if the sphere is white, you return white. What you do in this case is, instead of only taking the center of the pixel, you sum up all of these small things. Imagine they're infinitely small, subpixels. Then you sum them up, then average them. So the average of all these little colors will be the overall color that will be showing on the pixel. That way you gain smooth pixels, like these pixels are white, right? That is like gray area, then there's dark, there's more smooth. There's the transition is smoother, and it's more comfortable when you're trying to perceive the image itself. But we're not going to do that here, even though it's possible actually with the way we're doing things. Remember now, here's the hint for how you could do it. Remember, we're doing ray matching, and therefore we're kind of tracing spheres along the ray. The information you have with the spheres is that you can approximate the closest the ray has ever gotten to the sphere or the geometry you're rendering. Therefore, you can use it as some kind of you can compare the area here, or the minimum distance, with the projected pixel width out to the scene. Then you use that to determine the coverage of the scene. If how large is the geometry's portion that takes place that's projecting into the pixel, and how much of it is black. You kind of do a cone tracing process estimation and use that. Right? In this video, I'm just going to introduce the very simple concept. It's called super sampling. Super sampling. What does it mean? So what it means, it's a very simple idea. So instead of just projecting an array out through the center of the pixel, you project more rays within the same pixel, right? Then you compute the color for all these rays. Then you average them and use that as the final color of the pixel. It's kind of, you can think of it as an approximation of the cone tracing idea, which kind of is kind of like a Monte Carlo integration, right? We're approximating approximating the cone tracing color, and if we have enough samples and the samples are random enough, we can finally converge to the end result, even though the performance gets dropped. Right? So super sampling advantage is it's very simple. Right? It's very, very easy to implement if you can separate out the routine you do for each ray. But usually in the context we're in here, which is procedural graphics, of 4 times super sampling, meaning that for each pixel we shoot out 4 rays. The performance is going to be divided by 4, right? Because we need 4 times as many rays we need to compute, and these are the primary core operations that we have. So these are the operations that takes up the most time. It's slow, but it works, and it looks pretty good if you do it in the right way. Right? There are some papers that go into the study of what's the optimal pattern for gaining the best coverage and stuff like that. We're not going to go into that. Since I haven't talked about hash or random or noise, something like that yet, I'm just going to divide the pixel into 4 subpixels and center each of those 4 subpixels for that in this video. And you will see the result is much nicer than what we have right now, which, if we look through the magnifying glass, this is what we have. All right. So this is what we have. And why don't I opt the indirect light? I think that's a little dark right now. So 0.02. Let me opt the light a little bit. 20. Okay, 20 looks good. So you can see the the aliasing here. I already showed you that. Next up is let's re-examine our code. So we've obtained the coordinate, whichever coordinate of the pixel is at. Then we use that information to project, kind of this is the camera code we have. The essential output from these lines of code is the origin of the camera, which does not change based on where the pixel is. What changes is the ray direction, right? And the rest of these operations depends on these two parameters. So why don't we just go ahead and do that? Now remember, so say we've obtained multiple samples. Let's first think this through. What I'm getting at is, where do we average the colors? Do we average it here, or do we average it after the square root operation? Remember, operations or transformations are only, you can assume them to be linear when they're in linear space. And you cannot do the same in gamma space, because square root does not preserve the linearity in transformations. Therefore, it's a much safer bet to do it right before the gamma correction, because we're guaranteed to be in the linear space right here. All right. So the API of Rush much rather to have is UV. We've obtained the pixel coordinates. We're going to jitter it up a little bit. So sub UV, we do something like that. Then we do a for loop to loop through all 4 subpixels. And for each of these subpixels, it's going to be some kind of nested for loop. Then we do have some accumulator here, right? Color. This is going to be the total color. And the color add the render, which is the output for that particular pixel coordinate, for that particular subpixel. Then I average by dividing it by 4, because there are 4 subpixels. Okay, so that is the plan. First order of business is to kind of pull everything out into this render function, so that we can, we don't have to actually write this much code 4 times. Instead, we just call this function 4 times and average them. So let's go ahead and do that. All right, so render gives coordinate of the pixel UV. I was going to say something. There's actually an important decision to make. Right. So because we're going to be computing the coordinates of the subpixels, it's important to decide at which coordinate system we want to do the subpixel division. We could do it before the UV step, meaning we're going to operate on the fret core, which is the raw coordinates of a pixel that gets passed in. Now remember, these coordinates are in pixels. And after these two lines, the pixel coordinates have been turned into UV, which is in a normalized coordinate system. Right? There's a distinction of that UV has already been, normalized, meaning that the aspect ratio should no longer be. The aspect ratio has now become integrated into the coordinate system, which means that when we try to do the subpixel division or try to compute the coordinates for the subpixel, we have to take into account of the aspect ratio. And if we're doing it in the fret coordinate space, which is the raw coordinate space, we don't have to think about anything like that. So I would rather have the freedom of just do it in pixels, which is a lot easier because it's just, okay, I get the center of the pixel, I just move here by 0.25 amount, diagonally, and that's that. Move to the right by 0.25 and move up by 0.25. That will be the center of the right upmost pixel, subpixel, and the same operation can be applied to all the other subpixels to obtain these results. So I would rather do that. So why don't we change the render function to take the fret coordinate instead, right? So instead of doing this right now, why don't we just do color equals render, just to kind of test it out, to make sure the render function works exactly the same as it used to be before we pull it out. So let's do it in linear space, even right before the tone mapping, because that's what makes sense. All right. So here's the bulk of our computation, right? It is compiled and it looks exactly the same. It's very clear now, in order to do super sampling, we have to call render function more than once. And the bulk of the shader code is inside the render function, therefore, it's going to be 4 times as expensive to render the scene. I don't know why super sampling is not the most ideal anti-aliasing method, but it is the most simple, and it makes the most sense to beginners. Okay, so now on to subpixel division. So we're just gonna keep it color as an accumulator. We're gonna do y. We'll do 0 to 1. This is the y part, and this is x equal to 0, x equals to 1. So at each stage, these things are going to be iterated twice, right? So here's what's going to happen. We're going to run in the inner loop twice, and we're going to run an outer loop twice. Multiply these, we get 4 times of operations. That's just a simple sanity check to make sure that I'm on the right track. So we can assume that the fret coordinate that pass in through the main image function is the center of the pixel. And what we can do here is to, because each pixel is 1 pixel wide, half a pixel will be 0.5, right? Why am I using the mouse? I have a pen here. I bought it in the first place. So width is going to be, so pixel width, pw equals 1. Subpixel width is, of course, 0.5 because I've divided into 4 subpixels. Therefore, in order to move the centroid of the pixel onto any of the centroid of the subpixels, that means, well, we can kind of unroll the for loop here, right? Because we know how many subpixels we're getting at, so we just write 4 lines of render with the explicit offset for the subpixels. That should work just fine. So for the let's do it in a clockwise direction. So let's do the uprightmost subpixel first. So that would just be whatever, pixel position. Add 0.5. Let me just type it up. Just realized I could just type it into the code instead of drawing it. So color plus equals render fret coordinate plus G5, that's the rightmost. Remember, the coordinate system X is positive going to right, and Y is going positive going to the up direction. This is the first line. Second line is the bottom right. So I get a sense that you probably compute these coordinates yourself, so I'm not going to explain. It's a kind of redundant explanation. So for chord, it's going to be really bright because we did not divide by 4 yet. All right. Actually, you know what? This is super interesting. I'm not sure if you've read MPJ's article. I assume you didn't, but doing super sampling, or in the context of the article, was multi-sampling resolution, which is essentially what we're doing by doing divisions here. It should be done after the gamma correction, so even after tone mapping. So after tone mapping, after gamma correction, we do the super sampling. No. Only after tone mapping, because how do I put this in words? At the current state it is now, color is in linear space, right? These are going to be either super high values or super low values. They're crazy. They're assumed to be in a range of 0 to infinity. And after tone mapping, they're mapped to what's actually going to be on the screen, right? This is human perceived colors here, and these are not. These are not nearly what we get to see at the end. Believe it or not, multi-sample resolution, which is essentially what we're doing here, adding all these samples and average them. It makes a lot more sense to move after tone mapping, because we're doing the multi-sampling part on the color space that's much closer to what we're going to see, instead of in the linear space or in the HDR space, which we're not going to see on the monitor, unless you have an HDR monitor in this sense. So what we're going to do, this is going to be a little weird. So what we're going to do is, this is funny. So we're going to tone map all these colors. So we're going to do post each render. So tone map, we have some color, in HDR. We tone map it down to LDR. So I'm just going to copy the tone map code. Good. And here, instead, I'm just going to do tone map. I think if I compile this is going to get very bright, because I don't have the division and I don't have the tone map to save me there. But it's all right, because we remember this. We're going to do it anyways for ourselves. All right. So, and now we're going to divide by 4. The result, in my opinion, looks much better, right? Because the way we're sampling stuff, we still have a little bit artifact here and there, but that doesn't matter. We can do it. So let me just do a simple comparison first. So this is just macro. Right? This means I'm gonna. You know what? I'm not gonna explain it. That will be a waste of your time, probably. You already know. So tone map render fret chord. We're gonna compare it with the version without anti-aliasing on. Okay. So this is without anti-aliasing on. you can see the jagged edges. So keep in mind where you're seeing the anti-alias patterns, right? So keep those in mind. I'm going to switch to the anti-aliased version and look at these areas again. They're much smoother, right? The sampling pattern isn't exactly what I expected, but you can obviously see. You know what? I'm just going to take a screenshot at a similar region. I think I will do it in here. You know, this line is especially heavily aliased. So I'm just call this aliased. Switch to anti-alias mode. Anti-aliased, and we're gonna examine these two screenshots under our magnifying glass. Anti-aliased, aliased. All right, so aliased. Let's just delete capture. Don't need it anymore. You like how fast my operating system is? You like how fast the delete is? Okay. I love it. I love this operating system. So you can see this is I don't know what happened. No. The design of the software is great. So what just happened? Can you stop that? But do I have to? Huh. Oh, this is very interesting actually. How fucking dog shit this software is. Alright. So you can see the edges are I have to keep dragging this thing. So you can see how the edges are jagged stairs. There's a staircase effect, which is not very pleasant to look at, right? It's not good, not polished. But the anti-aliased version, you can see what I was talking about, right? Some of the pixels on the edge are, you kind of take a larger coverage of them, you know, shoot out multiple samples of rays, and then you average these samples to kind of mimic cone tracing. So we're taking into account the missing space that's also projected onto the pixel. So this is why when we look at this image, it looks much smoother. I still don't, there might be still something wrong with this. It looks all right to me, probably because of our sampling pattern isn't very good. You know, looks pretty good, right? So actually, I was holding down another topic, which is ray marching optimization. I missed my chance to introduce it first in the ray marching lecture, and I was kind of hoping that if we compute render 4 times, this performance will get a little, you know, slower on my computer, but it seems like my computer is too much of a beast, so I have to force the topic here. I kind of force it. So what I was going to say is that in our intersect routine, so where is it? So here, we're ray marching 256, 256 is our maxed iteration amount. And that is insane to do that many computations, actually, if you think about it. We have to compute SDF of here 256 times in a single pixel shader. For each pixel, that is. So this is not great, right? But luckily, when we shoot out our pixels, most of them will hit some geometry very early on, so iteration will be like around 10 to 20, right? But then if we shoot these out in the dark, say our camera is facing up in the sky where there's no geometry, we're basically wasting all that time we're iterating, right? We're iterating into infinity, which doesn't give back anything. So there's an early termination method for that, which not really a method, is more like a hack, which is to define the maximum distance that you want your ray to travel, which we already kind of set up for that, right? If you remember here, t divided by 30, here's the 30 is the fog distance. It's where if you went over 30, then the interpolation will return 0 for the color, meaning that any geometry beyond 30 won't be visible on the screen anyways because they're replaced by 0. So instead, what we can do is to make this tunable parameter, Pmax, we'll kind of make a macro for it, it's our global variable, So Tmax 30. Oh, someone's not happy. So 30 will be our maximum distance the ray travels. So what we can do here is if T is bigger than Tmax, we can basically say we terminate the iterations. After we terminate, assuming that we haven't hit anything, the mat ID will be -1, meaning that the rate did not hit anything, right? And that would be, that was the way we kind of used to see if the ray even intersected with anything. So we just break it out and we just end the iteration early, much earlier than we would have. And this will have no effect on the image whatsoever because we're using Tmax as the distance threshold for each ray. So you can see this is actually much faster now, you gotta believe me. The image is exactly the same. That's how you do ray optimizations. It's like a very small subset of the optimizations you could do. But here you go. So you can still kind of see, it's much smoother than before, but you can still kind of see some artifacts that's, affecting our renders. That's because we're only doing 4 subpixels for each pixel samples. And that is not great, You can see some game settings having like ×8 or ×16 multi-samples aliasing. Those are actually used differently because it uses rasterization technique. That means they translate the geometry into a lot of triangles, and the triangles are the ones that are sampled, multi-sampled, instead of what's actually rendered inside the triangles. Meaning that it does multi-sampling on what geometry you feed to the rasterizer. But here on Shader Toy, we don't have the luxury because, I believe it's done by feeding 2 giant triangles, and the actual geometry we're rendering has nothing to do with the geometry that we feed onto the GPU. That means we can't use MSAA, which is multi-sample aliasing. We have to do some kind of super sample aliasing, or we can just come up with some clever scheme ourselves, like approximating the cone tracing. So this is anti-aliasing. I believe this concludes the series that's called Procedural Graphics Basics. Unless I changed it later on, but this is going to be, I think, the final episode for the series. So hopefully you've learned something through the series. Hopefully you had fun, and hopefully you thought this was very useful and interesting, like I do. This is really fun stuff. Even though we've ended the series, this does not mean that this whole channel is going to shut down, because I have a long list of stuff I want to teach you. This is just literally the only basics to get you to where to get you to up to speed, for you at a position at which you can follow the more advanced series. So if you complete the series, pat yourself on the back. You did a great job, and you've learned a lot since you began, hopefully. All right, so this concludes the series and this video. Hopefully you enjoyed it. I'll see you next time.